Welcome, and let's look at revision questions in algebra. This part of the questions that I've given in my continuous assessment test. The first question is, if A is a 2 by 2 matrix such that the null space corresponding to the eigenvalue 3 is 3, 2. This is the eigenvalue. This is the eigenvalue here. 3 is the eigenvalue. And the null space corresponding to the eigenvalue, to the eigenvalue 5 is 1, 1. Find A. So this is a very easy question. We've been given the eigenvalue, and we've been given the corresponding null space. So that means when the eigenvalue is 3, the corresponding eigenvector is 3, 2. And also, when the eigenvalue is 5, the corresponding eigenvector is 1, 1. So then we are asked to find matrix A. So the first thing we're supposed to know is that matrix A will be given by P multiplied by D multiplied by P inverse. That's how we find matrix A, where D is the diagonal matrix, and P is the matrix formed when we arrange the eigenvectors as columns, so that the first column is 3, 2, and the second column is 1, 1. So this is P. And P inverse, we just do it by finding the inverse of P. So to find the inverse of P, first of all, we want to find the determinant of P, which is 3 minus 2. We now to find the determinant of matrix, and that will be 1. 3, this diagonal, the product of this diagonal minus the product of this diagonal. And so that is 1. So what is P inverse? P inverse is 1 over the determinant, but the determinant is 1. So 1 over the determinant will be 1 multiplied by the adjoint of this matrix. The adjoint of this matrix just reverse the elements in this diagonal, and then change the sign of the elements in this other diagonal. So the sign here is positive, we make it negative, and the sign here is also positive, make it negative. So this is P inverse. Now, so we already have P, we have P inverse. So it remains just to find D, the diagonal matrix, but that is very easy. So to find D, let me just create some space. But before I create some space, notice that this eigenvector here, the first eigenvector that we wrote in P, the corresponding eigenvalue is 3. And the second eigenvector that we wrote in P, its corresponding eigenvalue was 5. So we must note these orders. The order in which we wrote the eigenvectors will determine the order of the eigenvalues in the diagonal matrix D. So let me just create some space here and write. So this was a very simple question. So that means D, and we are following this order, the first eigenvector here, its corresponding eigenvalue was 3. So 3 comes first. And then the second eigenvector here in P, its corresponding eigenvalue was 5. So 5 comes second. So then this is D, and this is P, and this is P inverse. So now we just need to find A. So let me create some space again. Create some space. So now, what is A? We had already said that A will be given by P, D, P inverse. But we already have P. P was formed by writing these eigenvectors in column form. So P is 3, 2, and 1, 1. Then D, we wrote D by writing the eigenvalue corresponds to the first eigenvector, and that eigenvalue is 3, and cover the rest by 0. Then there's a 0 here. Then the second eigenvalue was 5. What about P inverse? Our P inverse was 1, negative 1, and negative 2, 3. So we then multiply these matrices in this order in which they appear to find A. So let's multiply the first 2 matrices. When you multiply the 3 by that gives you 9 plus 0. So that would be 9. Then 3 by that would be 0 plus 5. And then you have 6 plus 0, that is 6 here. Then you have 0 plus 5. You know how to multiply matrices. Let's multiply this by the last matrix, negative 1, negative 2, 3. And when you do this, you have 9. That is 9 minus 10, which is negative 1. Then I have negative 9 plus 15, which is 6. And then multiply that again, you have a 6 minus 10, that gives you negative 4. And then you have negative 6 plus 15, that gives you, that was negative 6. Negative 6 plus 15, that is supposed to be 9. So this is A, this is A. And that's what the question wanted us to do, to find the value of A. But there was nothing difficult with this question. You only needed to know that the eigenvalue 3, for the eigenvalue 3, the null space was given. So you are to get the eigenvector from here. And then also for the eigenvalue 5, the null space was given, and therefore you get the eigenvector for this. And then using these eigenvectors, you would get the matrix P. Then from matrix P, you would get P inverse. And it was easy coming up with the diagonal matrix D. And then use this formula to find your matrix A. That is what the question wanted us to do. So let's report the next question. Now we have this question, we asked to find this matrix raised to negative 3. Now it would be very easy to find this matrix raised to 3. There are 2 ways to do this question. The first question is to notice that this matrix can also be written as the inverse of this matrix and then raised to 3. That is one way of doing this question, that we will first of all find the inverse of this matrix. Then after finding the inverse of this matrix, raise it to 3. Raise it to 3. Or the other way would be to take this matrix, raise it to 3, and then find the inverse of the resulting answer. Now, so those are the two ways. These are the two ways you can do this question. First of all, we may want to find the inverse of this matrix and then raise that inverse to 3. Or we may want to find the cube of this matrix and then get the inverse of the resulting answer. I want to use the first option. So what the first option says is that I first of all find the inverse of this matrix. So let me just erase this. First of all, find the inverse, and then raise that inverse to 3. So let me find the inverse of this matrix. And I know to do this, first of all, I find the determinant of this matrix. The determinant of this matrix 4, 3, 1, 1 will be the product here minus the product here, which will be 1. That will be 4 minus 3 times 1. So that means the inverse of this matrix. So 4, 3, 1, 1 inverse will be 1 over the determinant, which is 1 out of 1, multiplied by the adjoint of this matrix. And the adjoint of that matrix just reverse the elements of this diagonal and change the signs of the elements in this other diagonal. So this will be -1, -3. So when you do that, what you then get will be 1, -3, -1, 4. So this is the inverse of the matrix here. Now, let's now raise this inverse to 3. So that means you just multiply it 3 times. Multiply it 3 times. Now, if you don't want to do that, supposing the power here was too big, then you would first of all discover that A raised to n, matrix A raised to n, would be P D raised to n multiplied by P inverse. So this we get this from the previous example, from the previous question, because the previous question is said that A was given by P D P inverse. That means that if I was to raise A to any value, then I would have A raised to n will be given by P D raised to n times P raised to 1. No, P raised to -1. And I've said that that is if this value was too big. But what I'm saying here is that just a very small value, so we just multiply it 3 times, and that will make our work very easier. So let's now do this. We're getting, I want us to get just erase this so that we can write here. So we want 4, 3, 1, 1 raised to -3, and you said it will be the same as 1, -3, -1, 4 raised to 3. Because we've already found the inverse. And this is the same as 1, -3, -1, 4 multiplied by 1, -3, -1, 4 multiplied by 1, -3, -1, 4. Because 3 is a very small power. Let me create some space here. So let's multiply the first 2 and so we get, of course, this you must do it in the order in which they appear. This times that, the result multiplied by this. When you do this times that, to be 1 plus 3, which is 4, and this would be -3 minus 12, which is -15, and this is -1, -4, which is -5, and then finally +1, +3, +16, which is positive 19. Then multiply this by 1, negative 3, negative 1, 4. And when you do this, what you then get will be 19, negative 24, negative 72, and then finally have 91. So you can multiply this. And this is how you do this question. And from the start, I showed you that there were 2 ways of doing this question. So I just chosen one way, but you could also have chosen the other way. Just look at the other question. Now here is the question. You're given matrix A, and you're asked to find a real value K if A is to be singular. And then B, we are told that if lambda is equal to 2 is an eigenvalue of A, then what will be the real value K? So K is here. So let's just do it. We need to understand what the question A is. Question A says that find K, the real value K, if A is to be singular. That means if A is to have a determinant of 0. If the determinant of this matrix is asking us to find. So just find the determinant that equates to 0. Now for this matrix, it's easier to find the determinant along this second column because it has zeros. I can see a 0, 0, then I'm only left with one value here. That means it's easier for me to find a determinant along this column. But of course, you know how to find determinant of matrices and how to simplify your workings, how to make it easier for you to find determinant. So, and you discover that whenever there are zeros in a row or in a column, then it's easier to find determinant along that row or along that column. Now, so this is positive, negative, positive, negative, positive, negative, positive, negative, and so on. So, you know, if this is negative, then this will be positive, and this will be negative. So those signs reverse, and we had already talked about that in my earlier video on how to find determinant matrix. Now, so you find a determinant along this column. So this will be negative, positive. And now I'm at this element. I want to delete this column that contains this element. Delete the column and the row, and then find the determinant of the matrix that remains, which is K, 1, negative 11K. Yeah, when you delete that, left will be K1, negative 11K. And so this is K minus 3 multiplied by the determinant of this matrix is K squared minus negative 11, which is positive 11. And we are told that this determinant is 0. So find the real value K. And I can see that if I was to equate, I'm supposed to equate this to 0 or equate K squared plus 11 to 0. So the first one here gives me that K is 3. And this is a real value, this is a real number. But now if I were to solve for K in this other equation, I would find a complex value. I will find a complex number, not a real number. So I don't need to proceed with this. I'll need to stop at this point, and the question is answered. Question A here is answered because question A wanted us to find a real number K that will give us determinant of 0 if it were placed here. So if you were to place here 3 where K is, then 3 here, and then 3 here, you would realize that this determinant would then be 0. Now let's look at the next question B. Question B says that given that 2 would be an eigenvalue for this matrix, determine the value of K. And again, the question wants us just to get the real value of K. Now, so this is an eigenvalue. What we know is that if we have matrix A and subtract lambda I from it and get the determinant of the resulting, the answer should be 0, where this lambda is an eigenvalue. That means that if I was to subtract this 2 from 2i, if I was to take A minus 2i and get the determinant, this determinant should be 0. And that will help me to get K. So let me see, what is 2i? 2i is 2 times 1. These are 3 by 3 matrices. So 0, 1, 0, 0, 0, 1. Where I is the identity matrix, a 3 by 3 identity matrix. So 2 times I would then be 2, 0, 0, 0, 2, 0, 0, 0, 2. So this 2i. So this 2i that I'm subtracting from matrix A, this is the same as subtracting 2 from this diagonal. It's the same as subtracting 2 from this diagonal. Because this 2 here will be subtracted from this K, this 2 here will be subtracted from this, and this 2 here will be subtracted from this. So it's equivalent to subtracting 2 from this leading diagonal. That means, therefore, that the determinant of A minus 2r will be the same as, if I subtract 2 from this leading diagonal, it will be K minus 2, 0, 1. And this will be negative 11. This will be K minus 5. And this will be 9. And this other one will be negative 11. And what about this? It will be 0, then K minus 2. Find this determinant. Find this determinant and equate to 0. And you notice that again, we have zeros along the second diagonal, the second column. So that again makes our work very easy. So let's find the determinant along the second column. Let's find the determinant along the second column. So when that happens, then we have K minus 5 multiplied by the determinant of the matrix that remains when I delete second column and the second row. So that is K minus 2, 1, negative 11, K minus 2. So when we delete that and that, K minus 2, 1, negative 11, it was K minus 2, yes. And this should be 0. So when you simplify this, you find here K minus 5, this is K minus 5, multiplied by this determinant, it is K minus 2 multiplied by K minus 2. Let me just put this other bracket here to separate these two. And then minus this product, which means plus 11. Close our bracket and equal to 0. So when you simplify this, you will find that K will be 5. You find that K will be 5. Because when you simplify this other bracket inside this other bracket and equate to 0, K will be a complex value. But the question only wants the real value. we'll try and simplify this. Try and simplify this at your own time. It's very easy simplifying this. Just multiply this bracket by this bracket, and then add this, and then equate to 0. You'll find that this bracket here will give you a complex value. Let's look at the next question. Now, the next question is very easy. The question is, let A be this matrix. If mu here is one of the eigenvectors of A, find the corresponding eigenvalue. And we know from introduction video that we had on eigenvalues and eigenvectors, we saw that matrix A multiplied by the eigenvector mu will be the same as lambda multiplied by mu. Where lambda here is the eigenvalue and mu is the eigenvector. So what that then means is that if I take this matrix A and multiply it by the eigenvector 2, 5, the result should be the same as eigenvalue times eigenvector. But let me just multiply this and see. This will be 34 minus 20, which will be 14. And this will be 60 minus 25, which will be 35. And so what this means, this should be the same as lambda multiplied by the eigenvector 2, 5. And when I look at this, I say that lambda here is 7, because this would be 7 times 2, 5. Lambda is 7. So that means the corresponding eigenvector value is 7. That's what the question wanted us to do. And we're just using this knowledge here. And this knowledge we acquired from our introductory video on eigenvalues and eigenvectors. Let's look at the next question. Now, this one is just a repeat of what we did in our introductory video on how to find eigenvalues and eigenvectors. So the question is, find the eigenvalue and the corresponding eigenvector. Now, to find the eigenvalues, what we did was, as we did in another example earlier, I subtract lambda here. Find this determinant and equate to 0. Let me say lambda I. Let me say lambda I. A minus lambda I, the determinant of that equate to 0. So when I do this, it will be 85 out of 14 minus lambda, negative 3 out of 14. And then this would be 5 out of 14. And this would be 69 out of 14. This is 69 minus lambda. This determinant equated to 0. And when you do this, what you get is a determinant. Just multiply this. Just multiply this. And of course, you may want to factor out 1 out of 14, but let's just multiply. This would be 85 out of 14 minus lambda. This is 14 multiplied by 69 out of 14 minus lambda. And then this is minus, this is plus, so the result when you subtract, the result will be positive, and this will be 3 out of 14 multiplied by 5 out of 14. And this is all equating to 0 so that we can get lambda. Now, so when you multiply using a calculator, you would find that these terms that will give you 58/65 divided by this will give you 196. And then when you multiply this other one, you have 154 lambda. Over 14. And this other one gives you lambda square. And I was also getting 15 out of 196. And this gives you 0. Just multiply this and that to give this times that times this times that plus this times that is what gives you 154 lambda out of 14. Then minus lambda times minus lambda gives you lambda square. Then this gives you this and equal to 0. Now, so at this point, you may want, because you want to, okay, these are like terms. Bring these ones together, this and that, bring them together. And so what you have is lambda square minus 154 lambda out of 14. And this other one gives you 58/80 out of 196. And equates this to 0. At this point, you can get lambda by using quadratic formula. Use quadratic formula. So let me just get some space. So what is lambda? By quadratic formula, it would be minus this, minus 154 out of 14, plus or minus the square root of negative 154 out of 14 square, minus 4 multiplied by 1, then multiplied by this 58/80 out of 196. So this is lambda out of divided by 2 times 1, which is 2. And you know how to use quadratic formula. So when you do this, you will find that you get 11 plus or minus 1 out of 2, which says that lambda is 5 or 6. So what's the question? Find the eigenvalue and the corresponding eigenvector. So that means the eigenvalues are lambda 1 is 5 and lambda 2 is 6. Now, so since we now have the eigenvalues, and our eigenvalues are lambda 1 is 5 and lambda 2 is 6, we now find the corresponding eigenvectors. And to find an eigenvector, what we normally do, we take a minus lambda I, multiply this by the eigenvector, and equate to 0. Then we use mu, eigenvector mu, and equate to 0. So I want to let mu be xy. because I'm dealing with a 2 by 2 matrix. And lambda here is 5. So I'll take a minus 5I and multiply by mu and equal to 0. So this is the same as subtracting 5 from the leading diagonal. So what I will then have would be 85 out of 14 minus 5, negative 3 out of 14, 5 out of 14, 69 out of 14 minus 5. Multiplied by xy and equal to 0, 0. Multiplied by xy is 0, 0. From here now we go to Gaussian elimination. Let's just go to Gaussian elimination now. Want to create some space. Negative 3 out of 14, 5 out of 14, and negative 1 out of 14, 0, 0. I want to make this a leading one. So I multiply row 1 by 14 out of 15. When that happens, you have 1 here, and then you have negative 1 out of 5, 0. And I want this other row to remain the way it is first. Because this was 14, not 4. It was 14. Having created a leading one in this position, I want to use it to clear this other element, make it 0. That means what I want to do is I want to get a new row 2 by taking the current row 2 minus 5 out of 14 multiplied by the current row 1. When that happens, row 1 remains the way it is, but now this becomes 0 because it's 5 out of 14 minus this multiplied by 5 out of 14. Now, what do you get when you multiply this? Now, when you take negative 14, negative 1 out of 14, and from this subtract negative 1 out of 5 multiplied by 5 out of 14. This gives you 0, because this will be positive 1 out of 14 added to negative 1 out of 14. This also be 0. So now what we now have is x minus 1 out of 5y is equals to 0. So from here, x here is a leading variable and y here is a free variable. So let the free variable y be t. Let y be t. If y is t, then x becomes 1 out of 5t. Just take this on the other side of the equation, because x is equals to 1 out of 5y. But y is t, so it will be 1 out of 5t. So at this point, we are now in a position to get the eigenvector. In a position to get the eigenvector, then we get space here. So the eigenvector will be in the form or any other multiple of 14 minus 6, negative 3 out of 14, 5 out of 14, 69 out of 14, minus 6. Multiplied by x, y, and equal to 0, 0. Now let's just simplify this first part and this other part. When you simplify that, what do you get? Let's subtract. So this gives you 1 out of 14. You can simplify that. And then this remains as negative 3 out of 14. This remains as 5 out of 14. And this other one is negative 15 out of 14. Multiplied by xy and equals to 0, 0. Now from here you can use Gaussian elimination straight away. So it will be 1 out of 14, negative 3 out of 14, 5 out of 14, negative 5 or 15 out of 14, 0, 0. And this time, I want to create a leading one here. Multiply this row 1 by 14. Multiply row 1 by 14. This becomes 1, and this becomes negative 3. And this row 2 remains the way it is, 5 out of 14. And then negative 15 out of 14. 0, 0. Now, having created that leading one, use it to clear column 1. Use it to clear column 1. So let me just create some space here. And this, what I'm doing, you've already done it. We've already done it before. So it's not something new. You know how to do it, how to use Gaussian elimination. Now, so we want to get row 2. So we take the current row 2, and from it we subtract 5 out of 14 of row 1. So when that happens, this will be 1, negative 3, 0, and this will be 0, 0, 0. So what we now have is x minus 3y is 0. X here is a leading variable, and y is a free variable. So let the free variable y be b. If that is the case, then x will be 3b. If this one crosses the equal sign, it becomes 3y. So x is 3y, but y is b. So x is 3b. So what about the eigenvector? The eigenvector was xy. So this would be 3b, b. Or if you want, just create some space here. If you want, you can write this as 31b. So the eigenvector is in this form. It is 31 or any multiple of 31. So I want to take this to be the eigenvector corresponding to lambda is equal to 6. And that is the answer to that question. That's how you want to do this question. Let's look at the next question. Consider the following linear operator G on R2 and basis S, which is given by the basis is given S is given by it. This is S given by that, and the operator G is defined as this. Of G relative to S. Find the matrix representation of G relative to S. Now, so how to do this, how we normally do this, just to remind you, we had done it before. What we want to do is to find G of U1. After finding G of U1, write this as a linear combination of mu1, no, this is U1 and U2. After that, also find the G of U2 and write it as a linear combination. Write it. Find. Write it as a linear combination of U1 and U2. So find the equations, find those equations, those linear combination equations, and then from those write the transpose of the coefficients. That is what we are looking for. Now, so let's now do this question. Let's first of all find the G of U1. G of U1 is the same as G of 1, 3, because U1 is 1, 3. So where there is X, put 1, where there is Y, put 3. So this would be 2 if I put 1 here. And if I put 3 here, it would be negative 21. So that gives me negative 19. And what about this point? Put X here. X is 1, that would be 4. And Y is 3, that would be 9. So that would be 4 plus 9, which is 13. Now write this as a linear combination of U1 and U2. To write as a linear combination of U1 and U2 is the same as finding scalars R such that R times U1, find scalars A and B such that R times U1 plus B times U2 will give you this G of U1. Now, so let's just multiply this. It will be R plus 2B is negative 19, and 3R plus 5B is 13. Solve this simultaneously. Solve this simultaneously. Solve this simultaneously to find R as I was finding R to be 121 and B to be negative 70. Negative 70. This is easy. It's easy solving this simultaneously. So that means that G of U1 can be written as a linear combination of U1 and U2. So, let's write it. G of U1, therefore, can be written as a linear combination of U1 and U2 as 121 U1 minus 70 U2. And I want to call this as equation 1. Next, let's find G of U2. and write it as a linear combination of U1 and U2. And then find equation 2. What is G of U2? G of U2 is the same as G of 2, 5. G of 2, 5. So let's put 2, 5. Where there is X, put 2. And where there is Y, put 5. This would be 4 minus that 5, which is negative 1. And what about here? Put 2 where there is X here and 5 here. This will be 8 plus 15, which is 23. Now write this as a linear combination of U1 and U2. That means find scalars A and B such that this will equal to R multiplied by 1, 3 plus B multiplied by 2, 5. Now, so this is same as R plus 2B is negative 31, and this is 3R plus 5B is equals to 23. Again, solve simultaneously. Or if you want, you can use reduced to echelon form or use Gaussian elimination. And to find, you will find when you do this, you get A to be 201 and B to be negative 162. So that G of U2 as a linear combination of U1 and U2 will be written as 201 U1 minus 116 U2. We are done, so we just need to write what the question wants us to write. Okay, I want to call this equation 2. Now, so we are required to find the matrix representation of G relative to basis S, and that is the transpose of these coefficients. So I write these coefficients, the first coefficient, these coefficients in column form, 121, negative 70. And for equation 2, I had a 201 and negative 116. This is what the question wanted us to get. So after finding equation 1 and equation 2, I just wrote the coefficients in column form. And again, these are the coefficients of equation 2 in column form. And we've answered that question. Let's look at the next question. These are similar questions, just the same as the one we already done. And the question is, consider the following 2 by 2 matrix and the basis S. We're given A and we're given the basis. Now, if A defines a linear operator on R2, find matrix P, find matrix B that represents, find matrix B that represents the mapping A relative to basis S. Just doing the same thing as we've done in question 6. What this question wants is for us to find A of U1 and write this as a linear combination of U1 and U2. And then find A of U2 and write this as a linear combination of U1 and U2. This is what the question wants us to find. Can you see here? Can you see and D? And then after doing this, we write this as columns, just as we did in question 6. So let's find A of U1. A of U1 is 2, 4, 5, 6, multiplied by U1, and this gives you negative 6, negative 5, negative 6, negative 7. Because this would be 2 minus 8 is negative 6. And that would be 5 minus 12. That would be negative 7. So now, this negative 6, negative 7, write it as a linear combination of 1, negative 2, and B, 3, negative 7. This gives you A plus 3B is equals to negative 6, and negative 2A, negative 7B is equals to negative 7. And solve this to find, when you solve this simultaneously, you will find A to be negative 63 and B to be 19. So that A of U1 is negative 63 U1 plus 19 U2. This is our equation 1. That is our equation 1. Let me create some space. So you have equation 1 there. So we need to find equation 2, and then we write the matrix representation of B. Now let's now find A of U2. A of U2 is 2, 4, 5, 6, multiplied by U2, which is 3, negative 7. And this gives me negative 22, negative 27. Just multiply. Just multiply this. Now, so negative 22, negative 27 should be written as a linear combination of U1 and U2. That means determine the scalars A and B such that A times this matrix plus B times this matrix gives you A of U2. And what this gives you is A plus 3B is negative 22, and negative 2A, negative 7B is negative 27. When this is solved, you get, when you solve this simultaneously, you get A to be negative 235 and B would be 71. So that A of U2 will be negative 235 U1 plus 71 U2. And this is our equation 2. This is our equation 2. So what is left is just to write matrix B. Because you already have equation 1, you have equation 2. So our matrix B would be the matrix formed when you write the coefficients in equation 1 as a column vector, and the coefficients of column 2 as column 2. So the coefficients of column 2 be written as column 2. And this is matrix B. This is what we were supposed to have done. Let's look at the next question. This is easy. We are asked to find the determinant of this matrix. There are various ways of doing this. I could find it along the first row, or the second row, the third row, or the first column, or the second column, or the third column. But since the second row has zeros, it becomes easy for us to do along the second column because it has more zeros. So this is positive, negative, positive, negative, positive. So positive 2 multiplied by the determinant of the matrix that remains when you delete row 2 and column 2. So that is 5, 1, negative 11, 5. So this is 2 multiplied by 25 plus 11. This is 72. It's 72. And of course, if you can check one of my videos on how to find determinants of higher order matrices, and so that you learn. So we just revising what you've done earlier in this question. So let's find D. Let's find the determinant D, and this is the determinant of I'm just writing these coefficients: 3, 2, negative 1, 1, 4, negative 3, negative 2, 3, 5. You know how to find the determinant of matrix. So this determinant is 78. Just find it. Next, let's find the determinant of dx. So for dx, we replace this first column by this. Replace first column, the column of, no, it's dA, not dx, it's dA. It's dA because I'm seeing A here. That this column has A, so it's dA. So replace the column of A with 1, 11, 1, 11, 21. And these other columns remain the way they are. Let me use this because you'll find it determinant. 2, 4, 3, negative 1, negative 3, negative 5. No, it's positive 5, actually. It's not negative 5, but it's positive. Because I can see it's negative 1, negative 3, 5. This is 2, 4, 3. This determinant, if you do it, you get negative 156. Let's find the determinant of dB. So we replace the column of B with this, but the other columns remain over here. So this would be 3, 1, negative 2. This one we are replacing with 1, 11, 21. But this one remains as negative 1, negative 3, 5. When you do this, you get 312. Next, let's find the determinant of dx, dc. So it's this column of C that we are replacing with this, but the rest remain. So 3, 1, 32, 3, 1, 2 remains. 2, 4, 3 remains. 2, 4, 3 remains. This will replace with 1, 11, 21. When you do this, you find this determinant to be 78. Now, so let's go to the solutions. What is A? A is the determinant of dA divided by the determinant of B. And this is negative 156 divided by 78. That gives me 2, negative 2. What about B? It will be determinant of dB divided by determinant of D. And the dB was given us 312 divided by 78. That gives me 4. Lastly, C will be determinant of DC divided by determinant of D. That is 78 divided by 78, which is 1. So these are the values of A, B, C. But the question wanted us to find a solution to this system. So what is the solution to this system? Just need some small space here. So the solution of this system is X, Y, Z, which is, no, not X, it's ABC. ABC, which is A was negative 2, B is 4, and C is 1. This is the solution to the system. So this system has one solution, and this is the solution. That is how we were to do this question using Cramer's rule. And again, you can visit one of our videos that we've done earlier on how to solve systems of linear equations by Cramer's rule. Thank you for watching our video. If you've not subscribed, remember to subscribe so that whenever I upload a video, you can automatically view it. Thank you.